Institute for Scotland welcomes you to this NMIS Insights online webinar. The title of this morning's webinar is Digital Twinning and Manufacturing, Improving Productivity and Efficiency and Reducing Waste. Next slide, please. Introducing the speakers this morning, I'm delighted to say that we have joining us Mr. Richard Miller, who is a Senior Research Engineer for the Digital Team in NMIS and also holds responsibility for our connectivity theme lead. We have myself, Sam Hume. I am the Partnership Development Leader for the Digital Team, and I'm delighted to say that we are joined this morning by Mr. Gordon Fleming, who is the Managing Director for Kigtek Solutions. Good morning. A few housekeeping rules to run over before we begin. This webinar is being recorded and will be made available on our YouTube channel. Your microphones and webcams will be turned off during the session to avoid background noise. You can type your questions throughout the session via the chat tool, and please do. Time will be allocated at the end for speakers to answer your questions. Use the hashtag NMISInsights for any questions on Twitter @NMIS Group. And please take some time to complete our survey that will be sent after the webinar. What is the National Manufacturing Institute Scotland? The National Manufacturing Institute Scotland is a group of industry-led manufacturing research and development facilities, where research, industry and public sector work together to transform skills, productivity and innovation to attract investment and make Scotland a global leader in advanced manufacturing. NMIS will increase productivity by reducing barriers to innovation, investment and increase manufacturing competitiveness, will catalyse job creation and strengthen supply chain links, will inspire and attract talent and equip current and future workforces with the skills they need and that businesses need, and will work with manufacturing businesses of all sizes in multiple sectors, providing benefits across the whole of Scotland. To that end, we are part of a One Scotland team. We are operated by Strathclyde University. We are supported by the Scottish Government, Scottish Enterprise, Highlands and Islands Enterprise, the High Value Manufacturing Catapult, Skills Development Scotland, Renfrewshire Council, and the Scottish Funding Council. The NMIS Group is a combination of core NMIS capability, specialist technology centres, and an active network of partners in the manufacturing community. In this infographic here, we see in the yellow the areas that are open now. We have our specialist centres, the Advanced Forming Research Centre and the Lightweight Manufacturing Centre. In purple, we have the areas which are currently in development, the temporary workshop space and the outreach via NMIS network activities such as this. And in pistachio and teal, we have our core elements, which are opening in 2022, and they are constituted by the Digital Factory, Collaboration Hub, and Manufacturing Skills Academy. And with all that said, without further ado, I would like to introduce our first speaker, Mr. Richard Miller.
Thank you, Sam, for that introduction. So I'm here to talk to you about digital twinning and cyber physical systems. So we'll get straight to the point. Well, what is a cyber physical system? Well, it's the fusion of virtual, digital and physical worlds. It's the end game to Industry 4 premise conceptualized in Germany's digital agenda in 2009. The outlying concept is to manage and maintain a system through a network of connected devices that's able to continuously operate whilst also adapting to external and internal influences with minimal human intervention. And it's also founded upon the 9 pillars of the Industry 4 paradigm. So how do we create a digital twin? What are the fundamental elements? So when we look at the 9 pillars on your on your right hand side, well, the first element really is to try and develop data acquisition methods from your manufacturing process or your system. So to do that, we need to look at how we do the Internet of Things, which is all about low cost sensors being connected through wireless or wired technologies. System integration, so that's more about looking at hard control systems, whether it's PLC or SCADA systems. And obviously, as we collect all this data, we need to make sure it's secure. Obviously, we're generating a lot of IP from your specialist or the specialist processes, so we want to make sure that's protected. So once we've collected all that, we need to transfer it. So again, we're looking at system integration. How do we connect through different comms protocols and network configurations? Again, protecting that so that the data is protected during transfer, but also looking at the eventual point where it's going to be stored around cloud computing services. Now, when we talk about data storage, cloud computing was something that came out really early, but obviously as technology's gone through the last 10 years, we're now looking at hybrid solutions or on-premise solutions, looking at edge technologies where we're compressing or removing data from the actual transfer of data, so we're not actually creating a massive data set back in the central storage area. And again, we need to protect that data because this is sensitive information for companies who are trying to be competitive in a globalized market space. And after we've collected that data and we've transferred it and we've stored it, we want to do something with it. We want to earn value from it. So we want to be able to visualize that, whether that's through simulations or augmented or mixed reality. We want to be able to capitalize on it and utilize it to make quicker decisions, have more capability to react quicker to certain situations. So that's really how the fundamental elements. So within NMIS and from our journey so far over the last 2 years, we've kind of taken the approach that digital transformation is quite central to cyber physical systems, and that can take sort of two forms within digital twinning, whether it's prescriptive or predictive. Now, I've kind of tried to break this down because digital twin has been talked about a lot in the last 4 or 5 years. So we think that within the prescriptive element, it's founded upon current technologies and engineering tool sets such as modeling and design. We provide additional context to these tool sets by deploying into VR and AR devices and applying data sets from the physical system. So what we're really trying to do here is to contextualize and visualize digitized representation of manufacturing facilities, equipment and/or processes. And as we do that, the next step then really towards a cyber physical system is looking at how we do predictive digital twinning. And that's really built upon prescriptive by analysing data sets in real time and automating control and the protection methods to keep the system running to optimum conditions. Similar concepts already exist, such as control alarms, control trips within PLCs and maintenance systems. But this predictive element is going a step further because we're identifying the root cause and close to real time and providing information to remote locations not within the plant so that organizations can adapt to a situation developing rapidly. And we want to then eventually do this automated, so with very minimal interaction from human presence. So digital twin again, so looking at how when you look at this slide in digital twinning. So this slide is really trying to provide an overview of a manufacturing system comprising of multiple elements. So within digital masters, that's where really our design stage, our planning stage, where we have our computer-aided design, we have our computer-aided manufacture, computer-aided engineering. We have our BIM models, we have our model-based definition and our virtual control system so that we can develop our fully industrialized manufacturing system, but in a virtual sense. And we can manage all that through existing tool sets such as PLM, PDM, and ERP. Now that allows us to control and manage engineering processes that oversee product assembly and maintenance throughout the life cycle of the product. It also supports impact for new product implementation and revision control. However, what we can also do within that sort of teal sort of coloured box you see at the bottom is we can start to develop our standard operating procedures here. with regards to fabrication, with regards to assembly, installation and commissioning. We can create digital work instructions for operators on how to utilize the system or how to build and assemble something. We can use AR and VR to show and train operators as this goes through. So once you've created and designed our digital masters, the next step obviously is to start creating our physical masters. So based on the design intent, we can look at the fabrication processes, the assembly processes, the installation, commissioning, and the control systems. So whether it's PLC and SCADA systems, or we are applying external sensors to existing legacy systems, or whether we're deploying new network configurations, whether that's Wi-Fi, LoRaWAN, narrowband IoT, we can really deploy lots of different types of systems. But what that also does is it allows us to deploy our digital standard operating procedures, our digital work instructions. It allows us to visualize data on that physical master as it's been created from the actual design intent. But at this point, we could also, feed back into our digital masters through an interconnected network to show the development of the as designed against the as planned or the as created. And what we're really trying to do here is, embed that capability to organizations within the supply chain. So as we get through the physical masters, we've done the assembly, we've done the commissioning, we've done the fabrication, we then go into execution. So talking about, training operators on how to use it, physically operating the system, creating data sets from the defined KPIs and KPVs, so that's process indicators and process variables, the data acquisition methods to actually acquire those data sets, transferring that into a storage solution, but also then looking at that cybersecurity element as well. So again, we have existing technologies in there, whether it's PLC, SCADA, external sensors, network configurations. But again, we can also deploy what we've already created at the digital planning stage as well. And that really allows us to embed digital technologies on the shop floor, and it allows us to reduce elements around paper waste, traceability elements as well. We can develop a lot of interconnected and traceable data sets and solutions. So as we go from execution, the next step really is, well, where do we store it? Is it on-premise? Is it cloud? Is it more about cybersecurity as well? So these things already exist, whether it's IoT platforms or local servers. But as the more devices become connected, the more devices are placed for data acquisition, the more risk there is for potential security breaches. So these upcoming ISO accreditation or ISO regulations and HSE regulations for organizations need to be really adhered to when you're deploying a type of system that's going to incorporate digital twinning and connectivity. And some of the sort of, and looking at storage and the challenge around, carbon emissions and the amount of data sets you have to store, there are technologies out there that are looking to streamline that. So looking at edge computing, where we're effectively stripping out a lot of data at the point of source and only sending metadata back to the cloud surface or cloud or on-premise platform. So that at this point, the edge device or the edge compute device is only needing to work with the necessary data to control the system. And I think that's going to be a really key technology requirement to achieve such a cyber physical system. So we've collected it, we've executed the system, we've collected the data, we're now at the feedback level. And this is all about how we take the data collected and visualize it, how we apply analytics to that data as well, to look at trending information, to understand where we can do multiple different data sets in comparison and look at those trends and look at potential failure modes. We can look at how we do and manage operational changes and how we implement those operational changes. So again, we have systems like that already. We have manufacturing execution systems. We have computerized maintenance monitoring systems. So there's technology already there that has existed for the last 20 years. But what we're trying to do is build upon that by looking at how we, do AR and VR and machine learning and AI to make it much more sophisticated and much more intelligent, that it becomes a level of automated control in the future. So where are we at the moment within NMIS? So we have the Future Forge around. So when we look at NMIS as a team within the digital team, we've started off the prescriptive digital twinning element. So within the Future Forge, which are one of our main R&D programs, we're trying to bring forging back into the 21st century, applying technology to capture black art of forging through digitization and data acquisition from machine and part geometry during the process, where I want to apply data sets captured from KPIs and KPVs and feeding that back into the modeling and simulations to verify that what we are predicting at the modeling stage is actually happening in the physical world. So that's the sort of goal that we're trying to achieve with Future Forge. Now, what we see here on the images within the left-hand side is we have the architectural BIM model and the sort of civil engineering and structural information deployed within a VR scene and a gaming platform called Unity. And what we've done is, on top of those architectural and civil engineering, we've deployed the CAD models provided by suppliers at every design iteration. So we have built a mature VR scene with a 100% representation of what we expect to see within this facility once it's completed. And that allows us to, do facility planning and ergonomics and health and safety. We can assess that virtually prior to committing to manufacture of major assets in capital expenditure. We can also look to, so once we've done that, excuse me, just take a wee drink. So as we've created this scene, we have deployed machine kinematics into all the different moving objects within the actual CAD models. And we've also applied physics to these kinematics to get as real life understanding of the potential failure modes between the manipulator and the billets coming out of the furnaces, and looking at the transfer and the movement. So we're really going into a really high fidelity, really high detailed level of engineering assessment to make sure that when we actually go to operate this for the first time, we're not expecting anything unusual. So we're really starting to look at that real engineering design and modeling. And what we've also done, as you can see again, is we've created certain scenes for facility operation that are going to be planned and assessed based on the simulations. We are doing operator training prior to commissioning, so we should have our operators working within this VR scene, utilising hardware in the loop to allow operators to control the manipulator within the simulation in the simulator, so that the operator has as close to a real life experience and training and understanding of the operation of the overall manufacturing system. What I wanted to show you here is if you don't have that level of detail within your architectural models, we can create facility models and 3D models using laser scanning and photogrammetry. So you'll see in the top, we have a photogrammetry model of the Ross Priory that's a building within the university, of Strathclyde, that we are looking to develop, a 3D model of it. We were asked to do that. So we used a drone and a camera, an off-the-shelf camera, to fly around and take pictures and then using modeling software to pull it together. At the bottom, we have a laser scanning of the lightweight manufacturing centre where our cask filling system was deployed for our facility planning and looking at water, electrics and air lines to feed to the system. So we wanted to look at where was the best place to put it. So you can see that image there. So we didn't have, in these two instances, we didn't have a BIM model that's currently what modern practices use nowadays. We had to create something, and there are concepts of doing that. And that allows you to start your digital transformation. It gives you some low-level digital knowledge and capabilities and processes going forward. It does provide highly accurate scans of the internal and external building features at low cost. You can drop in CAD models, and as you do the design matures, you can understand the impact around those changes. Again, as I've already mentioned, the facility planning prior to installation, understanding the ergonomics of the operator utilising the system and the facility. And then obviously, as we go forward, we want to start populating these scenes with data and context to create information for decision making from remote locations. And this is where we want to get to. So this is really our goal for the next couple of years, is how do we create predictive digital twinning? So we want to build upon what we've already developed within the Future Forge and the Cask filling project by adding in automated changes to physical systems through analysis of real-time trending data in the digital twin. But this becomes far more complex. Intelligence needs to be built into the fusing of the two systems. So although we are providing a digital twin with data, we have to give the digital twin context of what that data means, and that's where AI and machine learning comes in. Next step is really looking at technology of field assets. As we want to do automated changes, we need to really work to as close to real time as possible, so that almost the changes made are instantaneous to make sure that we protect our physical assets as much as possible. So how do we do that whilst also working with complex manufacturing processes? So we need to look at that technology development as well. And like I've already said, it really requires close to real-time analysis and close to real-time modification of system parameters. So constant challenges in there around latency of data, speed of data transfer and speed of analysis, and again, the equipment capable of modifying itself based on trending information from system performance. So what I'm going to do now is that I've come towards the end of my sort of element within this presentation, but what I'd like to talk now about is a case study and a project that myself and Gordon worked on over the last year or so around digital twin cask filling process. And really the background was we were working with industry partners to devise a digital whisky cask filling process that can save the industry millions of pounds each year. So the challenge around this is quite a traditional environment to work in. There's not that much level of digitization and digital manufacturing. We worked alongside the FRC, Diageo, Siemens and Kigtek. And the industry challenge was really looking at how we could improve productivity, but also at the same time provide consistent, precise fill levels. And obviously, we need to tackle this inconsistent filling level, which results to either overspill, underfill, and foaming, providing real-time data on the fill volume. And in that element, I will now pass on to Gordon, who's going to take over from here.
Good morning, everybody. So it's probably worth just saying a little bit about the project consortia involved. The project was driven through Innovate UK, and for those of you who don't know who Innovate UK are, it's a kind of government-sponsored element where their objectives are to drive growth by de-risking and enabling innovation. In essence, connecting businesses such that they can turn ideas into commercially successful offerings. And they do that by providing funding, but also providing a collaborative working model that you sign on to. So you can see from the diagram that our kind of collaborative partnership included 4 organisations. There was AFRC, who were the academia side, Siemens were the technology partner, Diageo were our industry partner, and Kigtek, who's with a small to medium enterprise. So clearly 3 of the 4 partners were household names. I'm sure everybody knows who they are. So maybe just give a bit more background to Kigtek. We're a kind of small to medium enterprise based at Strathclyde Business Park in Central Belt of Scotland. Very much involved in systems and information engineering. Very much the world of automation, and our primary market sectors are food and beverage and power. And effectively we can design, develop, install, commission and look after systems in those markets. The reason it's important to know a little bit about is that the project we embarked on from a Kigtek perspective would have been possibly unaffordable, and maybe at best would have taken significantly longer to achieve without going through this kind of partnership model. So next slide, please. The high-level requirements for the project at face value sound quite straightforward. You fill a cask, but you have to fill a cask without either overfilling or underfilling. The impact of underfilling is that when you have several million casks to store, that you store a lot of fresh air, and a lot of fresh air being stored costs money. Overfilling is clearly undesirable because it means that you're having spillages and you're losing some of your product. Other targets were that we to fill an American standard barrel which holds 200 litres in under 60 seconds, and that the equipment to be suitable for installation in a hazardous area. The last point isn't so much a requirement, but more a statement as to remind us what the problem is. The problem is that an American standard barrel, for example, is not standard. So casks are not uniform, and typically a cask's volume can vary by plus and minus 20%. And there's also a degree of a cask's volume can vary throughout its life cycle, depending on what cooperage works have been performed to over its life. Next slide, please. So digital twin infers that there's two aspects. There's the physical world and the digital world. So in terms of thinking about our digital world, the logical place to start is by looking at what our physical world may look like. So if you look to the left-hand side, we can see a traditional system for any kind of plant automation. At the bottom, you have the plant and machinery, which comprises things like vessels, pipework, and includes the products that reside in the vessels and pipework. Your next layer is then where you have your actuators and sensors, such as motors, valves, and instruments. Moving up the layers again, you would then have how the physical world connects to your automation platform. So it will be I/O systems and corresponding networks. Moving up again, you then have your automation system itself and effectively the control application, which would run the sequences on automation required. The next layer up then is the kind of operator visualization layer, the HMI or user interface, and that provides the interactive element, the man-machine interface. The last part, the very top layer, is indicated as cloud data. Effectively, in all plants now, we have a desire and a need to store mass data and then use that data, analyze it to provide useful reports. And that information is then kind of distributed in a safe way to a number of consumers. We can now think about how each of those layers would be represented in a digital twin. So if we move to the next slide, please. So starting at the bottom again, the process layer. So there's three key things we used at the process layer. Siemens NX product is very much a mechanical design tool, and it was used to design the mechanics of the rig and the lance. And just as importantly, as well as designing these elements, it provided a lot of the necessary physical data that's required to populate the process simulation. Easy, things like pipe sizes, pipe configurations. We then have AMISIM. AMISIM is the real modelling engine that we use to provide a high fidelity simulation. And in order to have a high fidelity simulation, it requires to be configured with lots of data. Some of it, as I said, that comes from the mechanical design, but also requires a lot of information regarding things like fluid properties, pump curves, valve details. There's then how that detailed simulation connects onto the next layer. So we used another product called AMISIM Automation Connect, and it provides the linking piece between the process simulation and going into the device layer. If we look at the next slide, please. So if you look at in the left-hand side is very much what you would see as a traditional P&ID for our filling rig. And on the right-hand side is the AMISIM graphical representation of the filling rig. So what you can see on the right-hand side, the items in blue are AMISIM objects. And you can see how these are kind of linked together to provide a kind of representation of the physical plant. You can also see that there's three blue circles towards the top mid of the right-hand side. And these are the kind of fluid objects. And again, these have lots of data in behind them that provide the necessary information for AMISIM to perform the fluid dynamic calculations. The items in red show the interface connections. So this shows how data is transferred to and from the device layer in this particular instance. Now, at face value, it doesn't look very complicated, but in order to get a high fidelity simulation, the devil's in the detail. So effectively, every mechanical element and every product property required quite a lot of information to be able to get the level of simulation that we're aiming for with the digital twin. It did take quite a bit of time to put together, but I would imagine that as you do more of these, then you would have more library elements that would improve the efficiency of putting together your digital twin. Next slide, please. The next layer up is very much the device layer. The simulation software we used there, it was Siemens Simit. It is actually worth noting that Simit itself can provide a degree of process layer simulation depending on the fidelity required. In short, we were looking for as a higher fidelity as we could achieve as part of the project, and that was why we chose AMISIM. And it's possible that in larger application, the process simulation would probably be shared between the two, leveraging the best of both worlds. Simit in essence provides simulation of plant devices. So for example, where AMISIM calculates a flow rate, it's passed to Simit via Automation Connect. Simit then takes this flow rate and acts like the flow meter. So in essence, it converts the flow to an analog signal as a flow meter would. Simit then also simulates how that information is passed to the automation layer. So it also provides a simulation of the I/O equipment and the corresponding networks. If we move to the next slide, please. The automation layer is back into sort of more traditional world, and in essence, this isn't a piece of simulation software at this point. This is the real thing. So, in essence, for the automation platform, we were using Siemens PCS7, and from a PCS7 perspective, it is unable to distinguish the difference between the real world and digital world. It provides the kind of ability to create sequences and control loops and a kind of user interface, SCADA, for those who are familiar with these technologies. And the way it operates is exactly as it would on a real plant. It also then meant that we could fully develop, test and pre-commission the control application as part of the proof of concept before building the rig. It is worth noting that we used Simit Virtual Controller, and that was purely a decision to minimize the amount of equipment we had to hold and manage. We could easily have used a real controller. If we move to the next slide, please. The last layer is the information layer, which again, none of this is a simulation. This is the real tools that you would use in a real application for these purposes. There was two products that were used here. One product was a Siemens MindSphere, which is a cloud-based IoT platform, and it's very much designed for mass data capture, analysis, reporting, and then onward distribution to consumers. We also use Kigtek's own Cask tech product, which is very much a Cask management solution, software-based again, very much aimed at storing and analysing Cask-related operational information and data. So things like Cask long-term performance and maturation loss reporting. Again, web-based for ease of distribution to consumers. If we move on to the next slide, please. So the pretty pictures, or maybe in the left it's maybe not quite as pretty. In the right-hand side is the graphical representation of our Cask filling rig from the mechanical models that we produced. And in the left-hand side is an actual picture of the Cask filling rig. The LMC is very much an industrial environment, so it's got quite a kind of cluttered background, but if I maybe point out a couple of reference points, you can maybe just about relate the two. So one of the reference points at the left-hand side, if you notice the position of the Cask, and you can just about see the lands coming out the top of the Cask and going slightly diagonally to the left as it rises to a red object. That's the fill closure valve. You can clearly see the IBC just to the left of that. And if you look over to the right-hand side where you can see the screen, just above the screen, you'll see the fat kind of tummy arrangement, which is the Coriolis flow meter. So you can, with time, you can actually see and you can very closely relate the two images. If we could move to the next slide, please. In essence, the project has been a great success, and effectively, by building the physical rig, we were able to prove that the digital twin did indeed properly represent the real world, and both systems performed remarkably closely. As part of the process, we have been able to develop a kind of highly accurate and repeatable cask filling solution with no under or overfilling. We bettered our target fill time by 33%, in essence filling casks in about 40 seconds. and we could see that the combination of this could offer a significant improvement to the Scotch whisky industry. As it happens in recent months, there's been interest outside the whisky industry. There are lots of other spirits that go into casks. So the potential saving is not just for Scotch whisky, and there's a potential market outside Scotland and across the world, from a Kigtek point of view, has made the whole exercise of doing a digital twin project really quite exciting for us, and see great value going forward. If we move to the next slide, please. So maybe summarising some of the benefits, as I indicated at the start, that this process of digital twinning and developing the cask filling product, this would have been cost, skill and facilities prohibitive for a company like Kigtek to undertake. So the Innovate project approach has resolved all those issues and has resulted in Kigtek having a commercially ready solution to take to market. That was intended to be brought to market at the World Distilled Spirits Conference, which was scheduled at the end of May, which of course in the current pandemic has had to be postponed, but we are in the process of releasing it digitally. It's also worth saying that since then we have become a Tier 2 member at NMIS because of the great value we see with the ongoing relationship and the ambition that's been driven through NMIS. So hopefully that was of interest, and I'll now pass you back to Richard.
Thank you, Gordon. So I just wanted to sort of finish off the presentation just by looking at some of the benefits of digital twinning. So we can work smarter, we can put a lot more planning in prior to committing. You know, we can de-risk capital investment when we know virtually the type of results that we're going to achieve to make it a viable option going forward. And we can develop and simulate our systems through these virtual processes, whether it's AR or VR, if it's just on PC or mixed reality. We can become more agile. We can predict and plan operations and maintenance activities based on current trends within the overall system. We can respond to critical situations faster, and we can have remotely connected workers working. And I think this is quite an important point, because with the current pandemic issue, access to sites and facilities are becoming more and more difficult. So with the opportunity to have a digital twin at one location and your physical system at another location, you're able to understand as close to real time what's currently happening. And also through digital technologies, you'll be able to connect with one single person at site and be able to guide them on how to respond to any situations. And, you know, we can deploy a level of continuous improvement to staff as well around upskilling them in software capabilities, you know, software development and new software platforms and working with these technologies. And you become more competitive now. Obviously, globalization and the challenges around globalization was a big thing prior to about 4 months ago, and now it's became a little bit different, but it's still a big challenge where we have to look at how we internally as a nation, how we are able to produce and export to global companies around the world. So if we can become more agile and we can work smarter and we have less time, you know, commissioning and installing and developing a physical system, then we can get products to the market quicker. And also through digital twinning, we can offer a more customized service offering. So looking at how we change business models from purely just product offering to product and service offering, and having that remotely connected to one another is something that really offers a lot of leverage and opportunities to existing companies who work in these spaces. And with those kind of comments, I just want to say thanks very much for listening. That's it from me and Gordon. So we're now going to pass you back to Sam and the marketing team within NMIS to talk more, and we can answer some questions.
Thank you very much, Richard, and thank you very much, Gordon, for your comprehensive, erudite, engaging and informative presentations. Throughout the we've received some questions, so if I might, I'd like to direct them to yourselves. The first question that we had was from Graham, and it was around digital simulation software. The question is, have you conducted research around the pros and cons of all software packages? And how did you choose a particular package for FutureForge?
It's a good question. The answer to the first question is I couldn't say, because that's working within a different team within the visualization team. So I would need to go back and ask that question. With regards to FutureForge, again, I can't really answer that question because I wasn't part of that team during the initial scoping exercise around the software platforms that were being deployed on it. So
Right,
again,
so-
what I'll do is we can take that on board and probably answer that question through an email private comms session.
Absolutely. Well, thank you for your answer there, Richard and Graham, and Daniel as well, because you've expressed interest. I've provided my email address there, so I can connect you with our visualization theme leads within the centre. Another question which we've just received is from Heather, and it relates to the length of the cast filling project and also the cost.
So the length was so the cast filling project probably started about 4 years ago in its inception, and it took us about 2 years to get funding for it. And then we decided that it was a 12-month project, and we were trying to achieve something very ambitious at the beginning of that, which was cyber physical systems. But at the same time, we also want to achieve digital twinning as well for cast filling to achieve operational performance. Now, we didn't achieve cyber physical system requirements, but that didn't mean we don't know or understand the approach that we need to take to get to that space and time, to get to that level of complexity. And that's something that I'm working on internally with Gordon and the NMIS team to look at how we can create a much more predictive digital twin model rather than what we see today, which is far more prescriptive. So we are developing that contextualization of data, and we are going to start developing the AI and the machine learning elements around how we can automate such a system. And that's something that we're now taking away internally and trying to develop opportunities for that to happen. With regards to cost, it's an Innovate UK funded project, so I can't really say too much on that, but I don't know, Gordon, if you want to add any comments to that.
Yeah, I can maybe say a little bit. It's maybe not quite answering Graham's question directly. I mean, both Simit and AmiSim, in essence, are simulation products, so we were able to compare and contrast them both. And what it does raise is that you need to be very clear on what your objectives of your simulation are, because to do an entire plant with a product like AmiSim, it's quite an onerous task, so it would therefore be quite a costly task. And that's why I said when I was talking about the potential using a combination of Sim and AmiSim, these things become consideration. That there are certain processes that maybe don't merit a kind of super high fidelity simulation. So you just need to be very careful about the level of simulations you try to drive towards. And I think that was one of the big learning points from Kigtek's perspective, is that you need to kind of only go to the detail where that detail brings value to your objective. Both products were interesting, and you're right, there's lots and lots of products out there, but the other thing that was a bit of a revelation as we went through the project was the higher fidelity, the extra effort and the extra information and detail that's required goes up quite significantly, regardless of the product, when you start to understand how these modelling softwares work. So I know it doesn't quite answer the question directly, but maybe thought it was worth sharing some of those couple of insights.
No, it's very pertinent, Gordon.
Very pertinent. Thank you very much, Gordon. And as I've said, please, if there's any way that we can follow up, please contact either myself, Richard, or Gordon, or in fact, in the chat box here, we actually have an email address for NMIS inquiries in general. I have one other question as well, which I believe will be aimed at you, Richard. And it is, how are NMIS going to drive digital twinning advancement across Scotland's manufacturing companies, both in the manufacturing environments and the products that they manufacture? Forgive me, a bit of a mouthful there.
It's a very good question. It's a very challenging area. We know that to support Scottish manufacturing, we need to engage with all the different sectors and with the different manufacturing companies of all shapes and sizes, and we are developing our SME engagement team. We are looking to try and bring more people in through events like this. So whether it's digital twinning or visualization or machine learning and AI, we are trying exceptionally hard to engage with the manufacturing sector in all different spaces. We do have a network and outreach team who are engaging with different universities, different innovation centres, and building up greater interconnected networks to engage with with companies who are looking to develop their digital capabilities. So we are working actively in this space already to do that and to engage in these with these companies.
Fantastic. Thank you very much, Richard. I suppose I would just have one question for myself that I would like to ask, and perhaps it would be, do you think that this work in terms of digital twinning can be applied across sectors, the benefits, and across industries?
Absolutely. I mean, if we're planning virtually and we're failing virtually, we're not committing any capital expenditure up front. So, or not all the capital expenditure up front, and that goes for every industry across Scotland. There's a certain amount of there's a certain amount of challenges we have to face, and I think in understanding what those challenges are and understand them virtually before physically, then we can reduce the time around installation commission. We can reduce any costs around any unforeseen expenses. We can reduce we can reduce the amount of inefficiency that staff are having to do to wait for parts to come in, to stop jobs. So there's lots of different soft benefits as much as hard benefits for organisations to look at digital twinning.
Thank you very much.
Can I maybe just add to that as well, Sam, that obviously we are involved day to day in the world of projects, and one of the things that digital twinning enforces is putting a lot of good upfront thought in to be able to develop the digital twin. That it's not unusual for us to be involved in projects where there's been insufficient thought put in advance of building a plant, which means that when you get to the point of commissioning the plant, there can be, it's not unusual for sort of a lot of last minute tweaks and changes having to get made. And when those tweaks and changes involve mechanical changes, they can be quite expensive and they should be avoided. So one of the advantages that I can see of is it enforces a really good discipline of making sure you've properly designed and understand how your plant's going to operate before you start building it.
I think I'd just like to touch upon that comment you made there, Gordon, that, obviously projects are, big beasts, and, depending on the organisation, depending on the customers you're working with, there'll always be stresses on the time frame to complete projects. That's where there has to be a level of due diligence before you go into this level of pre-planning, and you have to be comfortable when you promote this kind of methodology to potential customers that that you see the majority of work being done in the design phase rather than in the implementation phase, so that you're able to build a good business case for your cost offering or your product offering. I think is quite something that needs to be taken into consideration as an external influence. Is time. Time is always a challenge on projects. We found time on this project extremely challenging, but at the same time we were able to reduce our installation and commitment time on our test rig from normally about 5 or 6 days to about 2. So we were able to install, commission the system within a couple of days, and we were having casks filled really quickly, repeatably, to a very good accuracy.
Thank you both. And I think we have 2 more questions here, the first of which I think that I can answer, and it's directly to Daniel and Aubrey. Can members get involved and support the university outreach team? Absolutely, Daniel. And perhaps we could continue that conversation offline. Another question here we have from Andrew. Do you see potential use of DT, low volume, jobbing manufacture, or do you see its real benefits in higher volume or repetition manufacturing?
I could give you a bit of my perspective on that. I do see it in low volume. I mean, low volume manufacturing is implying lots of product or tooling type changes. So having a digital twin to be able to understand how your plant has to be reconfigured or changed between different product elements is quite an important thing, because I think in lots of places the transition between small volume items is the cost. So if you're able to produce a digital twin that lets you understand how those transitions can be made and managed better and reduce your kind of non-production time, that adds value. And that, you don't get that in high volume production. So high volume production is more making sure that you get it right, and once you've got it right, it stays right. So there is value in both types of manufacture.
Just to add to that, Gordon, if you're looking at low volume production, and there's always challenges around costs and low volume, you don't need to go to the level of digital twinning that we kind of talked about in this. You could purely just have a virtual scene with your facility, and you're able to move different items around, understanding what the impacts are and the time frame that it could potentially take to do that. So again, it comes down to that customization for digital twinning for different sizes of companies and the type of jobs that they do. There's not a standard way of doing this. There's always going to be a slight difference depending on the customer's objectives or the company's objectives or the way they kind of want to do it. So that also needs to be looked at, as well as the sort of strategic value of that digital twinning. What level do you get to what value it provides?
Thank you very much. Thank you very much. Well, I suppose it seems that we've run out of questions from the chat box, and I assume that means that all questions or any question that anybody did have has been answered, or they're really busy thinking about them. I wonder, in respect of any associated questions, Richard, would you be happy for audience members to contact you directly with questions around digital twinning and the project?
Yep, more than happy to receive questions, through email.
And Gordon, I suppose the same question to yourself. If anybody has questions in and around the project, are you happy to answer?
Absolutely, likewise, Sam. No trouble at all. And it's just a shame that we're in a world of lockdown, because people would also be more than welcome to come and see some of the technologies that we've been working with and see physical demonstrations and things. So maybe when we come out the other end of the pandemic, that offer can still be available.
A kind one, thank you. So a medium-term aspiration. That's good. Well, so all it remains is for me to thank our speakers, Gordon and Richard. Thank you very much. For me to thank the audience. Thank you very much for your participation and questions. Please, I do encourage you to contact Richard, Gordon, myself, or the NMIS inquiries team. There's an email provided in the chat box here. I'd like to thank the marketing team for having arranged this session. And finally, to remind everybody that this is only, sorry, forgive me, we have an entire series of webinar events, and the next session is coming up next week. So please watch this space. Thank you, everybody.
Thank you.